The first example taught whether a precipitation would occur or not. This second example talks how can we selectively separate things. This solution has copper and zinc ions. They've shown some pictures right here. You have to decide what order will you add specific reagents. So what happened here is they added hydrogen sulfide, they controlled the pH to be about 1, and what happened is the copper sulfide precipitated out. What they did is they then filtered out that solid, and they were left with a solution of zinc 2+ ions. Well, then what happened is they increased the pH, and then the zinc sulfide precipitated. That's what you can visually see. Now let's see what we can do with some calculations, all right? Selective precipitation that we just saw is also known as fractional precipitation. It's based on salt solubility, which you can imagine is the magnitude of the Ksp. You want to choose a reagent that forms a precipitate with either one or a few of the ions, and you want to filter out the solid. It is extremely straightforward when you have univalent solids. By that I mean silver is +1, all of these halogens are -1 because they all have the same Ksp expression. So when I look at these three items, this is going to be the least soluble, and it will precipitate first. That would be followed by silver bromide being second, and by silver chloride being third. Now, it's really not as simple as that, but in principle, this is how it works. Now, you know, there's many different types of ionic solids, and not all of them are one-to-one. So our second example tells you what to do if you do not have that one-to-one stoichiometry. The best way I can show you is by an example. So we have silver chloride versus silver nitrate. And what we have is we've got a solution of sodium chloride. There's our source of chloride. And we have a solution of sodium chromate. And here we have our ion, chromate ion. So what we're going to do is we're going to form silver chloride and silver chromate. We write their Ksp expressions. So I'm assuming that you can write the equations, you can write the expressions, you can find the Ksps, all right? If it's an exam, you'll be given the Ksps. What you want to do is solve each of these expressions for the silver ion. So you can see how much silver is necessary to precipitate each. You saw I drew a little arrow towards the number 2. Well, that's going to play a role in helping us figure out what to do. So when I solve for silver, for the silver chloride, it is just Ksp times the chloride concentration that is given, and we have it as 0.050 molar. When we divide the two, we get a number, 3.6 times 10 to the minus 9 molar. So I need to do the exact same thing to find the amount of silver in silver chromate. The big difference, yes, I have rearranged it, but since silver is squared in the Ksp expression, I must take the square root of my math expression here. When I do that, I come up with a value for how much silver cation is necessary. I'm continuing this on the next slide, but notice for silver chloride 10 to the minus 9, for silver chromate 10 to the minus 5. And that's what's sitting at the top of this slide. We are going to precipitate silver chloride first because less Ag plus is required, 10 to the minus 9 molar. This is also called the minimum amount of silver cation necessary for precipitation. Now, in theory, we will keep precipitating our silver chloride until the silver concentration is greater than 1.5 times 10 to the minus 5, then silver chromate is going to begin to precipitate. When we talk about these in a problem, we say the concentration 3.6 times 10 to the minus 9 molar, it's called the concentration necessary for the best separation. So looking at this, you can see any salt can be separated knowing the Ksps and running the calculations. And again, in theory. Things are not so pretty in practice. The farther apart the concentrations are, the cleaner the separation. So what do I have on the last slide? Well, I took the book exercise, sample exercise 1717, and you can read it for yourself, but it's the same sort of thing. What concentration of chloride is necessary to begin precipitation of each salt? What I did was I did the same calculations as I did in the previous problem, but I kind of presented it a little bit differently. The salt requiring the lower concentration of Cl- will precipitate first, and that's at 10 to the minus 8 molar. And that turns out to be, once again, silver chloride. It will continue to precipitate until you reach the chloride concentration for lead chloride, which is 10 to the minus 2 molar. Work it through yourself. You can hear me say it, but I think if you think your way through it, it's going to take you a lot farther.